classifier, this is an important question, why a classifier or a learner might have an accurate prediction on the training set. So when you're training it, remember, it's optimizing a function, it's trying to do its best on the training samples. You might get maybe 98%, 95% accuracy on the training set. But once you test it on the hidden test set, you might completely get a very different performance, like a poor performance. So what are the reasons that might cause such a flip in behavior of the learner? Okay, so I want you to take a piece of paper, write your name up, I'm going to collect them at the end, and think about, I'll give you just 2 minutes, think about classifier related issues, why a classifier might work well on training and fail when it is being tested on the hidden set. Okay, so there might be classifier related issues and data related issues. So far, just to give you a hint, we looked at data related issues. Classifier related issues, we're going to look at them in just a minute, but I want you to think about them. Okay, think about a possible issue. These are actually big problems because you would get overexcited when you see that you have a very good performance on your training data, thinking that your classifier is learning well. But then once you come to the real challenge and the real test, it fails. Okay, so guys, any ideas? So let's start with data-related issues. Why a classifier might work well on the training data and fail on the testing data.
Domain shift, maybe?
Yes, domain shift, absolutely.
There might be a dominating class which might unfairly bias the learner.
Very good. Imbalanced class. So the imbalanced class, right? So that might work, but you need to think about it. This is, questionable. Something to think about, right? Well, because when you're training, if your training samples are imbalanced, then it depends on how this is an issue, data-related issue, but it might be a data-related issue, but also it's a classifier-related issue. It depends on how your classifier will handle that kind of imbalance, okay? Right, so anything else? What about classifier-related issues?
Maybe overfitting.
Overfitting, very good. So we're going to see this, overfitting. The training samples. So basically it's trying to do its best, but it's more than its capacity. It's too much, it's too good to be true, right? So here, let's look at the problem of overfitting. So this is the second issue. And here, let's say the general assumption we make about classifiers is that once we train them well on the training data, they can easily generalize and work well on the testing data. But that assumption is not always true. So let's say in the first case, we have, this is our data distribution. We want to classify or distinguish between the blue dots and the red crosses. And we learn or train our classifier. And the line will be maybe around, let's say, right, like we plot it somewhere around here. So if we want to learn, so in this case, this is a big problem. This is what we call overfitting the data. Overfitting, it means that we try to exactly learn how to include each sample, each blue sample in the blue class. So our line might be, our classifier is here nonlinear, and it tries to follow, like to create the boundary between, the exact boundary between the blue set and the red set. But this is problematic because if you have other samples coming in, they might not fit into that distribution. That might locate, like for example, right here, if we have new testing samples, they might locate outside, right? So it might be something like that. So this doesn't make the classifier generalizable to other testing samples which are unseen. So this is problematic, and this is what we call overfitting. And generally, if the classifier overfits the distribution of the training samples, then you might end up maybe having a very, very high classification accuracy, like in the training stage, like 100% or 99.9%. So just be careful when you see such numbers. Like it might be just an alert sign. Now the second case is where we're plotting our line around here. So maybe something around like there, right? So this case is called underfitting. Underfitting. So these two distributions are not linearly separable, because a best line would be nonlinear, like a curve that will disentangle both of them, like separate them. But here we just plotted a line and said, okay, so this is our classifier. It has made a few mistakes, but it will make more. So this is, the case of underfitting. Now what we call the good case is when you have a relaxed constraint where you're doing something like that. So you're allowing for a few mistakes to exist, but the boundary is more like it's more flexible to accommodate new points, new testing samples. Okay, so it doesn't exactly fit the distribution, and it's not just roughly approximating it. It's doing its best to strike a good balance. Okay, so that's a good case. It avoids underfitting and overfitting. Now let's get back to this. So we've seen a domain shift, imbalanced classes. So this is another problem we might run into, overfitting the training samples. So when it comes to data related issues, so there are also we can think about outliers. So in the literature, there are two terms I would like you guys to remember, or two definitions. So there is what we call fracture between data, and this entails the domain shift. So you have a fracture between the distributions. If you look at those, so this can be seen as a fracture. It's like it's broken, right? The distribution of the training and testing set. So what is the definition of a fracture? It was introduced in 2011. So in this example, the fracture between data it doesn't include just few points. It's the whole training data set and the testing set. So there is a shift or fracture between them. So if we have data from a laboratory A, we call it data set A, and we derive a classifier from it that can predict its class accurately. So this is in the training. We trained on a first data set that came from lab 1 or lab A, right? Then what we do, we get another data set. So this is what we call a multi-center data, and when for example, you're collecting medical data from hospital 1 and then hospital 2, and believe me, this is a real problem. You get overexcited, you're training your classifier on your data that you've gotten from the first hospital, and then when you want to test it on the second data set that came from the second hospital, you can see that your classifier performs very poorly, so it cannot generalize. And this is very problematic if you want to build AI apps for doctors to use in real-world applications across all hospitals in Turkey and around the world too, right? So the problem is very big. Now here, so the second data set is not accurately predicted by the classifier we had previously built due to a fracture between the data of both laboratories, okay? So this is data fracture. Now we have something else that we call fracture points, okay? So this is a synonymous of what we call noisy points, outlier points. So if you just see this term, just keep in mind it means outlier. So these are points that lie far away from the main distribution of your data. So fracture points in predictive distributions and alterations to the feature space where a fracture is considered as the point of failure. So a fracture point is actually a point of failure in the classifier's prediction. So it's where you can spot them by looking at how the classifier performs on classifying them. Generally, it fails, okay? And also, they might lie far away from the expected norm, or they deviate from the mean of the distribution, right? So if you look at this case, for example, so if this is the distribution of my data, and now you know that we're talking about features, right? About probabilities and things like that. So this is, for example, a single feature, right? And here you have some points might lie far away. So these, we might call them outliers, okay? Or fracture points, right? Okay, cool. Now, let's look specifically at, so when we say data shift, remember guys, we're not talking about the distribution of class A or class B. Okay, we're not concerned with the classes when we talk about classification. We're concerned about the distribution of the training data and the distribution of the testing data. So there are many types of data shifts, and here there is one particular type that we call covariate shift. Okay, so the term covariate shift was first introduced about 20 years ago Shimodaira. I'm not sure I'm getting it right, but good work, where it refers to changes in the distribution of the input variables x. Okay, so here a covariate is a feature. So for example, what we have a vector x. So this is our sample, and the sample belongs to, in this case, RD. It has D features, okay? And each feature, we can call it a covariate. So I'll explain more because I will talk about covariance matrix. So in this case, what we see, we have two different distributions. So the distribution of feature X, the blue one, so that's the training data, okay? And then we have the distribution of the same feature X, okay, in the testing data. And you can see that there is a big shift between their mean. So one is centered at 0.5, the other one is 0.2. The standard deviation, the spread, the width of the distribution is quite different. So we call this a population drift or a covariate shift. So these are similar terms. A population, why it's a population? Because we're plotting the distribution of this feature across all samples. So samples are like, considered our population. And it's drifting away, it's moving, right? So shifting or drifting, same thing. Now, what is this distribution? You can see it's a Gaussian distribution. So in this case, we can define it using this function, right, p of x. So it's simply a univariate normal distribution of a scalar value x. Okay, so it's one dimensional, and this is, just the typical, very typical Gaussian function, okay? So what we have the sigma right here. It's like the standard deviation squared, it's the variance, right? And then what we have the mean of the distribution. It's mu. So, it's mu. So we have the mean of the distribution, or expected value of x. So expected value, it means like if we look at the feature x in our population, what is the most expected value that we think our feature x will take across our samples, or in our samples when we look at the yellow distribution? What is the most common or most probable, highly probable value in this case? Guys, if you look at the distribution.
0.5.
Yes, 0.5. So it means generally our feature, like the size of the nose, for example, is 0.5 something, right? If we want to classify dogs and cats. So it's just the most common or most expected feature value for our across our samples. Now, let's look at this. So here, for example, this is the standard deviation. So we call it sigma right there. So it locates generally around there. And like here, also our sigma. So this is for the training distribution, and this is for the testing. And you can see we have two different things. So the sigmas are different. The variance of the Gaussian curve, the distribution of the data is different, and the mean is different. Mean is different. It's shifted. So if the means are far away, there is a drift or a shift. And if the spread is different, so that's another thing we're going to look at later on, okay, in a bit. Right, so let's look at our curve, our nice normal distribution. So this is, the top value that might take the highest value, and then it goes like this. Okay, this is not very symmetric, but it should be symmetric. And you have, mu minus plus sigma around here, and then plus minus 2 sigma, standard deviation, right? So that's a normal distribution. Generally, features in real world, you can see like from just the exam example, and you can also plot the features for the data you have, they tend to follow normal distributions, right? So this is the easiest and most common assumption to make about the distribution of your data. But before making it, you can plot your data and see whether it fits a normal distribution or not, okay? Cool. Now, what we're going to do, let's look at the general case. So in this formula, what we have, our x is our feature vector, our single feature, one feature, okay? And this is, one-dimensional case, but this is why we call it univariate. So we have a univariable, right? But what if we want to generalize it to multiple variables where our x belongs to Rd. Okay, so we have many features. It's a high dimensional vector. So in this case, this is the formula we define for px, how we build a Gaussian distribution, not just in a two-dimensional space, it's in three-dimensional space. So you can see the nice distribution in 3 dimensions. So it might have different sigmas along different directions. So this is something you need to visualize in your head. So in like along the x1, it might be narrow, but along the x2, it might be very flat. So this is in 3D. But if you visualize it in D space, D dimension, where you can't really imagine, it's very difficult, right? So in this case, we have our vector belonging to Rd. And this is a what we call multivariate normal joint density function. So it's like it's the joint probability, because we're looking at what exactly here? P of x1, x2, right? xd. So we want to look at this measurement, our x vector, our observation, but it has many components, right? Many features. So it's very simple. So this here, in this case, we, instead of having the variance, we change it with a covariance matrix. So I'll explain how we get that, of what we call covariates or features, x1, xd. Okay, so this plays the role of sigma squared in 1 dimension. And we have, what we changed to is we added a transpose of a vector. So before it was quite simple. So it's just, x, it's just the norm, x, the distance between the feature vector and the average vector mu, the mean, the average, right? And what we have an inverse, the inverse of covariance. So I'm not going to go into details on how we derive this, so you can read about that, but we're going to use this formula now to learn our classifier, okay? So right here, it's very important to know that we assume that each feature, okay, xi, is drawn from a normal distribution with a mean mu I and a variance sigma I squared. Okay, so this is the assumption we make about each feature. But I want you to see in your head that across all samples, the distribution of all features might be different, right? So they might take different means at different variances. Now, let's look at we're going to walk through this step by step. What is a variance and a covariance matrix? So in this case, so these are what I plotted here. We have 2 features. So this is nice. Actually, the source is from Hadrian, github.io. So I will give you the link. He has a very nice tutorial on linear algebra and the notion of variance, covariance, matrix determinant trace. So if you want to refresh your mind, have a look at those. Okay. So in this case, what I plotted here is the distribution of xi against xj. So I want to explore the relationship between 2 features, random features I picked out of the D features, okay? And what we want to look at, if these covary together positively, negatively, or they don't have any relationship, they're completely independent. So the notion of a variance of a variable, describes how much it is spread out. So with respect to the mean, so we look at the spread of the data. Now the covariance, it measures the amount of dependency between 2 variables. So let's look at more examples here. So we have positive covariance and negative. So why we say positive and why we say negative. So what is a definition of a positive covariance between 2 variables? Let's look at this graph very closely. So let's say xi here takes this value, and then we want to see when it becomes larger, how does the other variable behave? Okay, does it become larger, smaller, it increases or decreases? So we look at the increase of this of the variable xi. So here it increased, right? And then we check the corresponding behavior of the variable xj. So we can see when xi becomes larger, xj becomes larger, right? And you can take any two other random examples, random points in this distribution, and you're going to find the same behavior. So positive covariance, it means generally when one is increasing, the other one is also increasing, but also when one is decreasing, the other one is also decreasing. So there is like, it's a correlated behavior. Now, for the negative covariance, let's look at this case. What do we have? So we have a point right here. Okay, so this is the first value that xi takes. Another one. So when xi increases, what happens to xj? So this is the first point. Okay, second. And we can see it is decreasing, right? So in this case, an increase in xi will induce a decrease in xj in the other variable. So that's a negative covariance, or vice versa. Okay? Cool. Now, how do we compute this? So this is a very simple example to just refresh your memory. So you guys remember all of this? Who remembers this? Okay, very few. Okay, I'm happy I've done this. Okay, so, right. So what we have here, let's look at this example, right? We have our matrix A. Our matrix A, what it stores? It stores the number of subjects. So these are our subjects, okay? So these are our samples. And in rows, and we have our features in columns. And we want to compute the covariance matrix of our data. Okay, how do we get that? So first, we compute what we call the variance. So here, this is the covariance matrix that we want to get. And first, we look at the covariance between the feature 1 and feature, for example, like in this case, feature 1 with itself. Like it's the variance of the feature, its spread, or its deviation from the mean across all samples. So, and then we look at the second feature, okay, the second feature vector, and we compute its variance across all samples, and the third one, and compute its variance across all samples. So how do you get this? So this is the formula. It's quite simple. So the variance of feature xi across data samples, we sum over j. So what is j here? J is the number of samples, and normalize, divide by the number of samples. The difference, the deviation from the mean. So the difference between xji, okay, so the first one, and the mean of that feature. So what is the mean of the feature here, if we look at it? So if we look at the first feature vector, so it's 1, 5, 3, right? So here, if we compute what is the average of these numbers across all samples? So remember, this is, first feature, and these are samples. How many samples we have here? It's just 3, right? Okay, so what is the average? 3, very good. Okay, so that's our mu for feature I. So this is our mu1. Mu1 equals 3. Now, what we do, we look at we compute the difference between each, between the feature value across all samples. So this is, x31, for example. So it's 3j is the sample number. It's the sample, the ID of the sample, or the number of the row, and I is the column. That's our fixed feature. So this is just, we look at each sample and see, okay, my feature I, how far it is from the mean. Sample 1, sample 2, sample 3, and we sum all of them, divide by n. That's the variance, okay? And then we put it there. So I would like you to write this down. What we're going to get here is quite obvious. We're going to get 267, but I would like you to write it down. This formula, just, try to find the the variance of x1 by writing it down. Very simple. Okay. So let's do this together in just 3 seconds. Or you can try the variance of x2 or x3. Up to you, okay? So it's the variance of the feature across samples. So the most important thing to notice here, guys, is this mean does not depend on J, right? So what is changing is only this quantity because we are looping over the J, right? The mean is a constant in J. It just depends on the feature or the number of the column. Okay, so let's do it together. So the first value that x1 takes is, so we have x11. Okay, so it's our feature x11. x11 is this first element, right? 1 minus the mean, 3. So the mean is a constant, so it's going to be 3 everywhere, right? Okay, and don't forget the square. And the second one, what is x? We have x21, x21. Second row, first column, it's 5. And then the last one is 3. Okay? Very good. Quite simple. Now, let's look at the covariance, right? So in the covariance matrix, what is the covariance? So the covariance here, we have the third, like feature number, vector number 3, like the third vector with the first vector. Or we can look at it the other way, okay? So it's 1, and here it's 3. So we look at the covariance between two column vectors or features, the covariance of two features across all samples, okay? So for example, we take the first feature, the green vector, and the blue one, the third feature, the blue vector, and we compute their covariance. So the covariance formula is quite similar actually to the variance. We're going to see their relationship is quite simple. So here is the same thing. We are summing over over all subjects. But what are we summing here? We are summing the deviation from the feature mean across all sample. So we have the mean of the first feature, the mean of the second feature, okay? And these, of course, do not depend on the samples J. They're not indexed by J, but we're computing that the deviation from the mean for the first feature across samples, the deviation from the mean for the second feature across samples, multiplying them and normalizing them, dividing by the number of samples. This is the covariance. So when you look at data distribution, you always need to think about the mean. So all these formulas, they're quite simple, but they revolve around the average of a feature, the average of, like samples. So the mean is very important because it defines everything, okay? So deviation from a mean. Okay, so if we look at this formula, we want to get the -2, for example, in this case, we're going to compute the covariance between the first feature x1 and x3. So we should get -267. But what should we put here? So I would like you guys to write it down, okay? By just looking at this formula. So the covariance of feature 1 and feature 3 across all samples is equal to, so how many samples we have? This is important. We're normalizing by the number of samples, right? And you need to compute the mean of the first feature, and also separately before compute the mean of the second feature. And then apply the formula. So it's quite straightforward. So we have the mean of the first one. So here it's 3. And then we have the mean of the second one. And then we're going to compute the deviation, right? So it's like first row, and then first row here, 5 minus 4. Then we look at the second row, 5 minus mean plus 1 minus 4. Third row. So that is our formula. Very simple. Okay, cool. Now, How do you get the variance from the covariance? If you guys remember, and don't look at your notes, right, what did we have in the variance? The squared, right? So, and the variance is located where? So here, xi and xk are completely different features, right? But the variance we computed for the feature itself, right? So, covariance of xi is, right? So what is the formula? So 1 minus n, we're going to plug this in, equals, so xji minus mu I times what? xj again I minus mu what? I. We plugged it in, so this is squared, right? It's very simple. Cool. Right, so now imagine if the mu I for each feature is equal to 0. So imagine if the mean, what we call the data is zero-centered, like the mean is equal to 0. So this is a very common assumption we make to easily derive mathematical equations and optimizations. Is like sometimes we pre-process the data, so we shift it in such a way that we make its mean equal to 0. What do we get? What is the formula here? So if we apply this to the covariance matrix, then it's very simple. So we're going to remove this because this will be equal to 0, right? So we will have xji times xjk. What does that remind you guys in linear algebra? Does it remind you of anything? Something we saw like years ago? Dot product, right? So that's the dot product. So this is exactly the mathematical definition of a dot product, but without dividing by n. So we normalize by n for the covariance generally. So this is a definition of a dot product. So you multiply this by, like these numbers, and what you're gonna get at the end is just a scalar. Okay, so what you guys, I would like you to do is like, look, there is a book called the Matrix Cook book. I will put the link. It has all the linear algebra formulae, from simple ones to very, very complex ones. So if you want to dive more into optimization in the future, so that is a very good reference. Okay, so this is the simple example of a dot product between two vectors, x and y. So you can see, we multiply those. So this is very simple, right? And then the third one by the third one, and that's what we get. So here, the last point before we take, let's say we're going to take a break in a bit. So if we start with zero-centered matrix, how to make any matrix zero-centered? So like if we start by how to make any matrix zero-centered, that's the first thing. Let's ask about, let us think about that. We subtract the mean. Very good. We subtract the mean from all the features across, like we compute the mean of feature I across all samples, and then take, the mean and subtract it from that feature. So it's we make it zero-centered, right? Very simple. So once we do that, then the dot product between the matrix and the transpose, and its transpose, will produce the covariance matrix. Okay? So it's quite simple. So the way we're computing it in linear algebra. So generally, this can be regarded as a pre-processing step. So center the data matrix at 0, then compute the dot product, and then you divide by the number of samples to get the covariance, right? Okay, very cool. Great. So one final thing, which is important. What is the dimension of the covariance matrix? Right here. So remember, let's look at this case. Okay, so, well, this is quite tricky case, but maybe this one is better because you have 3 by 3. What is the dimension of this covariance matrix? Remember, guys, these are the features, these are the samples, and a covariance, is it a covariance of samples? No, it's a covariance of what? Features. We always compute the covariance between feature xi and xj, right? And then we create our covariance matrix. So what is the dimension of the covariance matrix? Which means how many rows it has and how many columns. In this case, 3 by 3. So it's the number of features, right? So if we have D features, then your covariance matrix will be D times D. Great. Okay, so now we go back to this one, and right here, we can look at the formula. So this is the covariance matrix, how we define it. So this is, of course, the variance of feature x1, xd, and here we're going to have d1, which means, you know, row, the dieth row with the first column. And if we take any other, if we take row I with column j, so we're going to have, oh, no, so we're going to have, yeah, so somewhere here, well, let's put it this way. xi, x1, and in the middle it will be somewhere like covariance of xi, xj, okay? So it's quite simple. And what we can say just, you know, to make it simpler in representation, sometimes we can look at those values and represent them as variances, so sigma 1 squared, and this one we can make this notation. This is the same notation, so you might find this in different textbooks, so they use this quite frequently, okay? Great. So I think we're going to take a break.